So welcome to today's rendition of TEOS. Our speaker is Professor Ron Cohen from Berkeley. Ron grew up 45 miles or so west of here in Brooklyn. Went to Wesleyan University, that's somewhere in Connecticut, right? For his undergraduate degree, and then moved on to do a PhD at Berkeley with Rich Sakeley, working on one of my favorite molecules, an important molecule that everybody here in Soma cares a lot about, water. After his PhD at Berkeley, he then spent four-ish, maybe a little over four, closer to 5 years at Harvard, working in Jim Anderson's group, where everybody always learns a great deal. And he then went back to Berkeley in '95, roughly, to start his academic career in both chemistry and earth and planetary sciences. So I've known Ron a long time and always been amazed at how many different things he's doing and doing them really well, being a global leader in the field of atmospheric chemistry broadly. His group has done an awful lot of work working on studying nitrogen chemistry in the atmosphere in multiple phases, how that nitrogen chemistry connects to both ozone and aerosols. He's done a lot of biosphere-atmosphere interaction work, looking at biogenic volatile organic compounds, satellite remote sensing. He's a key player in the upcoming TEMPO satellite launch that is any day. Is TEMPO any day?
First 2 weeks of April.
That's coming up, and that will be a big deal for all of us. He's also been working on studies of greenhouse gas emissions and what we can learn about sources of greenhouse gases and the fascinating world of legislation and targets and the interaction between the science of seeing how are we doing and how that feeds back to the people who are implementing legislation and targets, and he's doing that in multiple continents now. So I won't steal his thunder for his talk. Let's welcome Ron to Soma.
Thank you, Paul, for the invitation and the kind introduction. Yeah, so let me start by saying that a while ago, one of my colleagues said to me, we should figure out some way to do something new and different. And I thought, okay, so what might that be? And stewed on that for probably a decade before I figured out something that was new and different, at least in the way he was suggesting. He was suggesting that our friends in computer science had strategies for tiny little radios so that we could sprinkle smart atmospheric sensors everywhere. And I think we're getting to that point where we can think about what we can learn from having large numbers of sensors in ways that are different than the small, excellent sensors that we might put in one spot. So what I want to talk to you today is thinking about what it means to make a map of the air and how we might use that to learn about the chemistry of the atmosphere. Okay, so let me remind you, in other places where I show this image, no one really knows what it is. Here you should recognize the George Washington Bridge. And I talk to people that we've made an enormous change in the air. It's not just in Los Angeles that we've cleaned the air. We've cleaned the air here in New York. When I was a kid growing up here, you couldn't see across the river often, and now you can almost always see across the river. And so the guiding questions that guide what the fundamental science we're trying to do are really questions at this intersection of air quality and climate. So, why is it that air quality is poor on a hot day? We spent a lot of time in my group thinking about the temperature dependence of chemistry and emissions in the atmosphere and how those intersect. And then turning to what I'll talk most about today, how do we understand the drivers of the planet getting warmer in terms of how do we understand CO2 and how do we track the changes in CO2 that we'd like to see happen and support the public and the political community in making changes. So let's get that. The experiment I want to tell you about is the Berkeley Environmental Air Quality and CO2 Observing Network. And I'll show you a set of observations laid out in the Bay Area of California. So here's a map. The city of San Francisco here, that's about 10 kilometers across. Berkeley is over here. And we're going to put observations in this urban area from about over here in the city just south of Oakland, all the way up through and across the bay to Vallejo, so at the top of the slide, and then a few on the eastern edge of San Francisco. And what you can see, among other things you see in this image is the topography of the Bay Area. So there's a set of hills over here. Those hills go up to about 1,400 feet. They rise pretty, as you can see here, they rise pretty steeply from the more or less sea level city. But before we get back to the observations I want to tell you about, let's think about other ways we use maps in atmospheric science. So here you have a map of the column of NO2. So this is the amount of NO2 between the surface and about 15 kilometers as seen from space. And this is what it looked like in 2005, 2006. And here in 2012, 2013. And this is a story of the intersection of regulation and technology. Mostly what you see here is that our chemical engineering colleagues built much, much better three-way catalysts to go on the back of gasoline-powered cars. Really much, much better, because in 2005, they were already pretty good devices. And between 05 and 12, every new car had a third generation catalyst, and the amount of NO2 in our cities dropped dramatically, about 7% per year. And the other thing you see is that many of the coal-fired power plants had controls put on them. Here's one. That one is the Four Corners power plant. It's two 500 megawatt boilers in a coal-fired power plant. There's lots of others. Ohio River Valley is littered with them. So we do have the capacity to make enormous changes in the atmosphere, and you can see them when you make a map. There are other kinds of maps we make. So here's an example of the observations of air quality around the San Francisco Bay Area. Just a few different kinds. Up at the top of that map where you see all those red hexagons, that's where most of the oil refining to make gasoline is for California. In that region, they remove the sulfur from the fuel because the sulfur poisons the catalysts that reduce the nitrogen oxides. When that's not working, smelly gases get released and the people in the neighborhood are upset. So there's often a mapping of sulfur gases around those refineries. And that's what all those red circles are, red hexagons. There's much more extensive air quality measurements made at the blue circles. You can see they're of order 20, 30 kilometers apart. Annoyingly, if you're trying to think about the intersection of meteorology and chemistry, which we always are, because they're intimately linked in the atmosphere, they don't measure the weather at the same place where they measure the chemistry. It's fundamentally crazy. It was none of these things were designed with the idea that someone was going to be thinking about them like a scientist. They were designed thinking about them like a regulator. So it didn't matter that you didn't measure temperature where you measure the chemistry, because the temperature never violates a standard. It is what it is, but the chemistry can violate some regulation. So just some examples. This is an example that goes far beyond what I'll show you in terms of making a map of air quality. There's a company called Purple Air. They've taken a pretty beautifully manufactured light scattering sensor for aerosol. The sensor, they say they measure a lot of stuff. The scientific literature shows that they measure particles between 300 nanometers and 1 micron quite well. It's light scattering, so they measure some overlap function of the index of refraction of the particles and the size of the particles in that size range. But they sell them for $100 or so, $200 to people. Every time there's a big fire in California and the winds are blowing in the reverse direction. I mean, most of the time when there's a fire, the winds are blowing towards you. So the fires are in the mountains to the east of me, and you smell the fire and I don't. But once in a while, the fire blows back the wrong way, and we get it. And every time that happens, someone else on my block buys one of these things. So there, you know, in the half mile of my street, quarter mile of my street, there are like 7 measurements of aerosol. Those of you who make measurements like this will know that that's kind of crazy. We don't need that for any kind of science, but it's an incredibly dense map where rich people live.
They're networked.
They're networked. You could go to Purple Air on your phone right now, and you could pull up in real time here where there's a crazy high number of them, or just about anywhere in the world they've been selling. So they're networked, they're in real time. It goes on the Wi-Fi in your house, it beams back, and they're plotting them and making them available.
As long as we're blurting out questions,
please.
What are the people in your neighborhood doing with the information? What actionable information?
So if you're measuring aerosol, like, I think they're feeling like more secure that there's a measurement that supports the fact that they want to put on their mask because it smells like a fire outside. It doesn't. I don't know. You know, no one is really doing anything with them except that they feel good about it. It's a measurement, and that's, you know, if you think about what's going on in the environmental justice communities, where there's a tremendous amount of belief that measurements are more believable than people. So people will trust a measurement when they won't trust something else. So it's reinforcing their own interpretation of the world when they see the measurement at their house. But, you know, to follow up on the other part of what Paul said, please, everyone else blurt out questions. Happy to, you know, make this more of a conversation. Okay, so we took a compromise somewhere in between those different kinds of maps I showed you. We looked at some, and so every green dot on this image here is a place where we're making a measurement right now, all simultaneously, mostly on the rooftops of schools. We were thinking about, if we want to understand the chemistry and emissions of a city, how close together do the measurements really need to be? And we looked back at some Gaussian plume theory that's sort of in the back of Seinfeld and Pandas, one of the later chapters. Early stuff looking at just, you know, how far should a plume spread if you emit something in a city? And then we looked at some more recent experiments that Suzanne Paulson at UCLA did. Suzanne and her group took in some aerosol measurements. They drove perpendicular to a freeway in LA on a day when the wind was blowing perpendicular to that freeway. And they found a 1/E length scale for the aerosol decay into some steady background of about 500 meters, 700 meters. So that gave us this idea, and it's consistent with most sort of urban Gaussian plume parameterizations that say roughly on a length scale of about 1 kilometer, if you're within 1 kilometer of a source in a city, you should still see something that's true to that source. And after that, it's more mixed and diffuse. So we set out to put our measurements every 2 kilometers, so we'd be within 1 kilometer of every source. And that's roughly the grid you have here. We tried to not put things much closer than 1.5 kilometers and not much further than 2.5, but the realities of the real estate that's accessible imposes some variability on that. But you can see we did a relatively decent job of filling the flatlands in the area we're trying to measure. So I should say, if you don't want to go to the Purple Air site, you could go to our site, beacon.berkeley.edu, and the measurements we're making will also be showing there on a map in real time. Make a movie of the last 2 weeks while we talk. So this is mostly a science experiment, but it's got all kinds of interesting public intersections. We're on the rooftops of schools. We try and talk to science teachers in those schools about curriculum that might use these measurements. We have a couple of instruments on the roof of the Exploratorium Museum. I'll show you those in a few minutes. And while we were doing this at the Exploratorium, they had an artist in residence who decided he would try and make music based on the aerosol measurements we make. And they were some public place where the bells would ring in proportion to how high the aerosol sounds were. So what are we measuring? The instrument we built is a shoebox-sized package that has it. So it has in it a CO2 sensor. That's the core instrument. Has 4 electrochemical measurements for air quality, CO, NO, NO2, and ozone. And it has an optical particle counter, exactly the same one that's in that Purple Air device, manufactured by a company called Plantower. And the CO2 is a commercial instrument, a non-dispersive infrared instrument. So what we've done here is nice packaging of a bunch of things that people are selling as OEM parts. We put it together with the power supply in a waterproof package, with the computing to store and organize all the data, and goes on the Wi-Fi of whatever building we're on, and transmits back in near real time as long as that Wi-Fi is working. We can build these for about $8,500, including some costs for the back end computing, and all the data will automatically stream to us. And the literature is filled with this conversation about low-cost sensors. I just remind you that the expensive part of science is the people. So the equipment is some part of the cost, but really, very rapidly, the cost of doing this project is the people who have to think about the measurements. And so we could spend a lot more on instruments, and it would still be the cost is the people. So don't get taken in by this excitement about low-cost sensing. We're still all high-cost people. And it's these people. This is a team, some of whom have gone on, some who are still working with me, the team that's made this work. This was a beginning of a good idea about a decade ago, and it's really hit its stride in the last 3 or 4 years. And lots of people worked on it in that intervening. And so I'll tell you about some of their work as we go along today. So here, I told you we were on the roof of the Exploratorium. That's the Science Museum in San Francisco. This is one of the few places where we broke the 2-kilometer rule. The building that the Exploratorium is on is 300 meters long. We put one sensor on the street side and one on the bay side of that building. They both are part of a display inside the museum, along with all the other measurements. And so here you get a sense of scale. This is our box. The Exploratorium has all kinds of other folks who've given weather station components to them. And just to remind you, in that first slide I showed you that we live in a place with topography. Here's for your sense of scale in meters above sea level. Most of our sensors are pretty low to the ground, and a few of them are quite high up on schools that are at the top of the East Bay Hills. And those couple sensors that are at high up mean that they're occasionally above the marine layer as it comes in. So they're seeing clean air that get in those moments is pretty disconnected from the city below them. Okay, so let me show you just a sample of the measurements. So here's measurements from 2018 through 2021 at about a dozen different sites. More than that, you can't see much. You see, if you go along the bottom of this trace, you see the northern hemisphere background CO2. That's a seasonal cycle driven by photosynthesis in the summer and respiration in the winter, or at least net differences in those two things were the relative importance changes. And then you see that in the winter it's cold and mixing is lower and concentrations at night go really high. So these extremely high values, 600, are not numbers that occur when the air is stagnant. And this is one of the hardest things about studying the urban atmosphere. The highest concentrations you measure will be on nights when it's cold and the air is not moving very much. And those high concentrations will occur even though the emissions will be down by a factor of 100 from what they were during the day. You might see 100 times higher concentration when the emissions are 100 times lower, because mixing is so important to what we observe.
What's the time resolution of the graph?
The time resolution of the graph is limited by the printer, but these are individual nights. The time resolution of the measurements that go into the graph is less than a minute. So here's just a higher time resolution of some subset of that data, just to get a flavor and to remind you that what I want to talk to you about today is how we learn from the variations within the map, not how we learn from the average of the map. So here's four schools. They're 1, 2, 3, 4. And so you click on those schools on our website and you set what dates you want to look at. And the website will have a trace like this. And you can see at the start of this, 3 of the schools were low and there was a higher CO2 at this site. And then you go along and the weather changes and then a different weather and we get a bump here and the green site is seeing more of that one over there and again. I should add that over here is the Chevron refinery. 1/3 of the total CO2 emissions in our domain come from that one refinery. That's a big source. I think the stacks are here and mostly the wind blows that way. So mostly we don't ever see that. Okay, so there's a lot of work that goes into thinking about how you can calibrate 50-odd sensors in dozens of locations when permission to bring bottle reference gases to those sites would be challenging to get, and where the labor of having reference gases at every site is inconsistent with the idea of having a network that you can operate at low cost. So we've done a bunch of work, and here I'm just showing you the results of it, calibrating the 4 electrochemical sensors for NO2, ozone, NO, and CO. And we can get reasonable measurements over the network. The calibration ideas rely a lot on finding moments when all the sensors should be seeing the same thing and dragging everything to be the same at those moments. Here's, we've done similar things for the CO2. And this is just an evaluation. One thing you can say is, on average, at least, nearest neighbors should be pretty identical. And so if we look at a nearest neighbor difference overall, the whole data set, that gives you some measure of the precision of the overall instruments. And so the variance is about 0.007 fractions, so of order a part per million, 2 parts per million accuracy. in the at least relative accuracy across the whole network. So we have measurements that are good enough for purpose. There are 50 of them in the domain I showed you. And that's roughly one observation every 2 square kilometers. And what you can think about this is, so the average of all of 50, the square root of 50 is a pretty good number. So we should have a good average measurement. But we also have details that we can think of as many, many small footprints. So each sensor is more sensitive to its nearest neighborhood than it is to things that are further away. And so there's information, they're all seeing the global background, but they're all seeing something local. And so that's where the excitement comes in. So that's the instrumentation. And now let's think about some reasons we might want to do this. Other than that's because it's fun and interesting, which is really why I want to do it. So in California and here in New York and all over the world, there's a growing set of legislation, policy, enforcement aimed at bringing us to net zero or maybe even net negative CO2. Put the amount of CO2 in the atmosphere back where it was 50 years ago, 100 years ago. And so in California, the first real serious law in this matter was in 2006. It was Assembly Bill 32, and it said we were going to reduce CO2 to 1990 levels by 2020. And then it became clear that wasn't going to be enough. And so then other bills, and today the current legislation says net zero by 2050, I think, or 2040, and no fossil fuel powered cars at all by 2035. So lots and lots of very aggressive actions. So we might ask as atmospheric scientists, are these the right aggressive actions? Can we show that they're working? What might we do to sort of track it along if we're going to try and change emissions and get to net zero in 20 years? So that's something like on average dropping 5% per year. That's not a small fraction. We should be able to see that. And we should be able to report that, if you only get to 2% this year, you better have a plan for accelerating in a few years. Or conversely, if the mayor runs by saying they're going to reduce emissions in their city, we should be able to provide them data to say, I did what I said, or so that someone who's more aggressive can say, you didn't do what you said. Here's the observations that show it, and I will do it. So what does that look like? In California, it looks like this. Some more than a third of the emissions in 2015 had to do with transportation, and then another big fraction from industry and energy production, and then a bunch of small things, buildings, from short-lived climate forces, and agriculture. California did hit that 2020 target. That was the early easy stuff. But getting down here, and now the new law says get to zero, you can imagine how hard that is. So the city of Oakland did its part to think this through. They had an internal climate action plan, and they said, well, if we look at 2050 and only take business, what the state has said it's going to do, we're going to get halfway there. So they said if we want to get towards net zero, the city has to do a whole bunch of other things in addition. So this top pink line is the state, and this green line over here is what the city said it was going to do. So we've been looking at this and independently sort of thinking about observations and how observations might intersect with this. So you might say, so what are these things? So the state controls things that have to do with transportation and cars. The federal government controls things that have to do with transportation and trains. And airports are somewhere in between. But cities control buildings. They control zoning, they control what. So things that have to do with, are we going to stop natural gas in all new construction? Are we going to stop natural gas in existing construction? Are we, what kind of electricity are we going to allow buildings to use? Those are the kinds of things that are in the purview of cities. And those are the kinds of things that drive this enormous difference here. Local actions are going to matter. So in this context, Oakland and lots of other cities are trying to put together their greenhouse gas plan. And they do that, and they all think they're doing it according to a script from the United Nations. And so you could ask, that's good. Everyone should be able to do the same thing with the same script. Kevin Gurney at Northern Arizona University wrote this really nice paper where he used one script for the whole country and built an emission inventory at city scale for every city in the United States. And then he got 50 cities to say, here's what I did. And he just did the comparison. And you can see in this map, red is different by a factor of 2, one either too much or too little. And so all these people who thought they're doing the same thing all these people who were trying to do the right thing. This is not people who were trying to cheat or be in violation. These are people who were trying to lead and be compliant. They're all over the map, literally and figuratively. And even so, here's Oakland, where I live. Oakland looks perfect on this map, but it's perfect for the wrong reasons. It happens that and I should say, this is not to say that Kevin Gurney's inventory is right, just to say that it's a uniform reference standard. So, any one of those other cities might be doing it more correctly, but we're trying to figure out one way that we can compare place A to place B, and so having the uniform standard is useful. So compared to Kevin's uniform standard, Oakland has 60% different construction vehicle transport, off-road transport emissions, and 20% different stationary sources. We should be able to do better. Those are big differences between two ways of counting CO2 emissions. So that's the sort of the policy background in mind. And I'd say, from our goal of supporting policy, what we'd like to be able to do is, in a few months' time, tell you whether a policy, what effect current policies are having. So what I'll show you now is a COVID-19 example where we shut down, as you know, we stopped going outside for a few weeks in April. In the following November, we had published a paper in the peer-reviewed literature saying how much CO2 emissions had changed. So we knew an answer in 3 months because there was peer review in between. So just take this as evidence that we could, in principle, within 3 months, quarterly report with very little lag the emissions that just happened inside a city. So the way we do this is by trying to improve on an initial guess of emissions. The initial guess is often called a prior, it's a prediction or a hypothesis. And for the most part, it doesn't use anything about the atmosphere. It uses economic data, social data, maybe a little bit about the weather. We heat our homes more when it's cold than when it's hot, so we should be emitting more CO2 in the winter than the summer, that kind of information. And what we're going to do is some kind of a fusion of that initial guess with the observations to have an output that's an optimization of the initial guess. And again, both for the state of California and for the county where most of our measurements are, you can see the similar kinds of balance of what the sources of emissions are. Transportation is a big fraction, and electricity and industrial, the other terms. So let's start with our initial guess, our CO2 inventory. In this case, this is a third inventory I'll show you. This one we built ourselves. You can see from in the middle of the night, what you mostly see are the stationary sources, and they're they're almost all off scale because they're a single point. It's tricky to figure out what they are. They're reported at corporate headquarters for most of these places, which is not where the staff's doing the emissions are. So this dot here at Chevron really belongs over there where the cooling water is, for example. But over time, we've gotten those in the right place, and you can see in the morning rush hour that emissions are on the roads, not surprisingly. We do see in our network, here's an example of the Chevron refinery plume. So at this time of day, the winds were coming here and they weren't going across the refinery. So all three of these sites look steady. And later on, the wind shifted and we're working backwards in this map from this receptor, getting pretty close to that site. And you can see it hits first that site, then the next one, then the next one. So the air is swinging around and bringing you across all three of those. And then later on, we're seeing those again. The other thing we need as part of this analysis, because CO2 is not just emitted, it's also removed by the biosphere, is some way of estimating what the biosphere is doing. There's a pretty beautiful measurement on the TROPE-OMI instrument, a European instrument flying in low Earth orbit, measuring what's called chlorophyll fluorescence, SIF, solar-induced fluorescence in lingo. And so what that's doing is when a green plant absorbs light, often it's using that light to turn CO2 into a sugar, but some small fraction of that light is actually converted to some other frequency and re-emitted as fluorescence. And it happens that some of that gets back to space and you can see it in space. Really extraordinary. And you can do that with incredibly high spatial resolution. So red here is when there's more in 2019 and blue when there's more in 2018. And what you see here, for example, are three locations where there were massive forest fires in California. In 2019, there was essentially no photosynthesis in those areas. By the fall, there was the same photosynthesis again as 2018, basically saying that, as seen from space, the grasses and shrubs that filled in those places ended up taking as much CO2 out of the atmosphere, well, at least looking in space as if they were taking as much CO2 out of the atmosphere as the forest that had been there. So we can do that, and we can use this to get to quite high resolution, so we can see the parks inside the city in this way and get a really good daily initial guess or weekly initial guess photosynthesis. So what we're going to do is we're going to take 6 weeks before the shelter in place and 6 weeks after and run this inverse model to do an iterative improvement on the emission inventory. It happened during spring. So we'll pay attention to the fact that the trees were doing more photosynthesis in this second period than the first. And if you're reading the literature about the COVID period, you should pay real careful attention to the fact that the world was not constant in all other respects except COVID in these 12 weeks. And there's a ton of literature that says, something was really different in that period. And really what was different is the weather was unusual and not the emissions. All over the world, especially in the nitrogen oxide literature and the ozone literature, it happened to be warmer in that period. So in lots of places in the world, there was more ozone in the COVID period because it was warmer. And so people said, even though we went home, ozone didn't get better. But if you had thought of it as a control experiment where you said the same temperature as the relevant day a year before, ozone was better. It was tricky because the weather changed a lot. So we'll pay attention to that here. And what we're doing is really solving an enormous matrix problem. It's basically in essence, we're doing a least squares fit between every observation in those 6 weeks. And so we average them to an hour first. the 6 weeks before the shelter in place and the 6 weeks after, and our emissions. And then we're at each point running the weather backwards to say, where did the air come from? And building a stochastic model of where on the surface the emissions came from and adjusting the emissions so that they match those observations as best as possible. And to do that requires a bunch of understanding that allows us to build the matrices that allow us to do this analysis, know something about the measurement error, something about the model error, and something about where we have sensitivity. So our conclusion after looking at all of this is that we're getting good information about emissions within this funny white contour. That's in the language of the inverse model, that's 40% of the influence is within this white line. You can see the intensity of the influence. You can see it's sort of dark purple, sort of near every measurement. And then, that if you live here, this whole shape of this might strike you as odd, might strike you as very odd that we have a measurement here and we're learning nothing about that side. There are really strong, persistent westerlies in the San Francisco Bay Area. The wind is whipping through here, through the Golden Gate, and that's the source of all wind. So even though this is 12 weeks of measurements, we learn almost nothing about the area that's just slightly downwind of us, because the winds are almost never reversed. In the same way I sort of mentioned to you early on in the talk that if there's a fire in the Sierra Nevada, which on this scale would be over on that wall, we almost never smell it here, even though you'll smell it here. We almost never smell it right there, even though you'll get it, because the westerlies are just so strong. Okay, and then there's one other piece of trick here. We're trying to, some of the information is, I don't want to say redundant, but it's interrelated. So that number of cars on the highway at exit 256 are pretty close to the number of cars at 257. So we should have some correlations in space, because we're not allowing CO2 emission to vary freely and completely independently. And we know that emissions now are sort of somewhat similar to 3 hours from now and somewhat similar to tomorrow at this time. And so we build correlations in space and time into the analysis as additional constraints. But if we just did that as a matrix and didn't do anything fancy, it would be unacceptably large. For the size of the analysis we're doing, these 6 weeks before and after, it would be a 374 terabyte matrix. We couldn't store that, let alone manipulate it. So we've separated the space and time parts of this as a way of keeping the data analysis manageable. What that looks like is, again, we're sort of high correlations now and an hour from now or an hour ago, decaying quickly, and then additional correlations 24 hours from now and 48 hours from now, because individual days are somewhat self-similar. And then we have correlations in space, but the spatial parts of the matrix index don't map so nicely, so you don't see it in the matrix the way you see it in time. So my former postdoc, Alex Turner, worked this out. Alex is now a professor at the University of Washington in atmospheric sciences there. So let's just look at the average over the domain. Here's the average CO2 before and after. You can see the change was not subtle. You can see there morning rush hour, enormous drops. That's what's maybe most noticeable, but even midday, there's lower CO2. And the same is also true of the carbon monoxide. Really big changes in carbon monoxide, and carbon monoxide is not as affected by the biosphere as CO2 is. Just a reminder that the first sanity check, that something really did happen. And what happened is that the cars and trucks on the road changed dramatically. And we're lucky enough to live in a place where the traffic management people are really into measurements. There's 18,000 measurements in the domain I showed you of traffic flow. Sensors on the highways, just an overwhelming number of measurements. And at some of those locations, they're measuring what's called weigh in motion. So they're measuring not only that a vehicle went by with a magnetometer, but they're measuring how heavy it is. So then they give you the cars and the trucks separately. We took a place on the approach to the San Francisco Bay Bridge, and here's what happened to vehicle miles traveled, based on that set of sensors. You can see before the pandemic, we're going along, and you can't see that says 10 to the fifth, 10 to the fifth vehicle miles for cars, and then it dropped down to somewhere over here, 4-ish. The trucks they're an order of magnitude less, 6/10 to the 4 on a weekday, about half that on a weekend before, and then afterwards they dropped some and even more deeply on the weekends. Okay, so the inverse model, which doesn't know what happened to all those trucks, gave us this answer. It said that CO2 before the pandemic had peaks of about 600 tons of carbon per hour in the domain, and after the pandemic, about 400 peaks of about 400. That almost all the change happened in the pixels that have highways. So what you're seeing here is the total CO2 in the domain, and then we took each pixel and we assigned it a source. We said if it had highway in it, it was associated with traffic. If it was a source if it was your house or my house or the refineries, it was a stationary source. And if it was a green pixel, that was forest or grasslands, it was the biosphere. The biosphere we fixed at what we observed from space. And then we subtracted that from the total to get these other terms. But you can see really what changed most amazingly was weekday traffic. People were still driving on the weekend. They were still getting their groceries. They were still doing other things. The weekends didn't change as much. Nighttime changed a lot. Many, many fewer people working nights and going out nights. If we put that on a map, and so it's my student Naomi who did the CO part of this. Here's a map of the CO2 before the shelter in place. You can see the roads are the hotspot, and you can see the big changes are on the roads, especially at the approach to and from this main bottleneck, the San Francisco Oakland Bay Bridge. That shows up here the difference. You see that the difference in CO is more diffuse. We're still working on what that means. One plausible hypothesis is that most CO2 emissions are first thing in the morning when catalysts are cold. There's good evidence that before the catalyst on your car is hot, as much as half the total CO2, carbon monoxide emissions that you will emit with your car happen in the first few miles driving from your home. So that would put the CO emissions in places that are not on the highways where the CO2, most of the CO2 changes. But it could also be if we just don't have the details right for CO. CO is harder. You can try and do this by time of day. And so you can get the pattern there. And you can confirm that the CO is telling us mostly the same thing by day of week. That we're seeing here this red line at 2.5 tons of carbon compared to like the CO2 was 400, CO is 2.5 in the same units. And you can see before the shelter in place, the carbon monoxide was typically, the traffic related CO was typically about 3 in midday, and afterwards it's about 2.5. A substantial reduction. So that was quick. And again, the paper on the CO2 was published 6 months after the event, sort of giving a little bit of evidence that we can do this and provide real-time feedback to policymakers. But we're also interested in much longer term change. Right? We're not going to get to zero in 6 months as much as we might like to flip a switch like that. So we want to track weather things over time. So here's an example of 4 Aprils, 2 years before the pandemic year, and then the year after. And that's what we see for the average CO2 emissions in the area in April. The other way we can do this is we can look compared to 2018. To the extent that this is almost all about cars, you can think of this graph as 1 over the change of fuel efficiency. And it's about, here it is, 3.3% per year. In 2020, it looks really different. The reason it looks really different is probably because the cars that stayed on the road were people who did not have university jobs and drive electric cars. They were people who were working in McDonald's and were driving much older cars that are less fuel efficient. The trucks stayed on the road. If you divide by the total number of vehicles on the road, you don't correct for the trucks. And probably in this analysis, some of the stationary sources are leaking into it. So we haven't fully figured out how to pull out the stationary sources. But ignoring that, this is really remarkable, and it's consistent with lots of other analyses that say this is approximately the rate of improvement in fuel efficiency in the region. New cars, which are electric at about 8% last year or the year before, were new cars, and so that doesn't translate into 3% increase in fuel efficiency of all cars, but it goes a lot in that direction. So I showed you some things about mapping. I showed you we can say things about emissions by sector in aggregate. I showed you that we can make a map. We might be able to tie that map to issues of environmental justice. In our case, that'll play out near the Port of Oakland. There's lots and lots of heavy duty diesel trucks at the Port of Oakland, and the people who live near there are people who are living the after effects of redlining. So it's both racially divided and economically poor compared to the rest of the area. And they're far more exposed to the effects of diesel, nitrogen oxide, and aerosol emissions. This is one example of something we might do. I just want to show you a couple of ways we're thinking about other kinds of analyses of these observations. Because we might like to not just know the total, we might like to know something about the process that's responsible for emissions. So I showed you that we have all this great data for the cars. We also have the speed. One question we asked is, do the emissions depend on speed? Right? And so we'll take a look at that. And we'll start here. We'll start with a different way of getting at the vehicle fuel efficiency. So instead of the big fancy inverse model, we did a simple analysis where we took every site in the network and we asked a multiple linear regression to think about it with some weather variables and the number of cars on the nearest highway. And what we got out of that after removing the weather variables is this incredible correlation between what we'll call vehicle CO2, but it's the residual CO2 after removing effects for weather, and the number of vehicles per unit time on the highway. It was linear, but it was a different line at every site. So we knew that was saying, okay, you have some information, but we didn't know how to put it all together. And it took us a few years to go back to this Gaussian plume idea and say, what we should expect is that the influence of the cars on the road should be high near the road and should decay in the way the Gaussian plume does. So when you did that, when you take basically the slope of that line I just showed you from every side in the network and plot it as a function of distance from the highway, you're super sensitive to the one site that's nearest the highway. But on average, we see something that sort of plausibly behaves in that way with 1/E lane scales of roughly what we expect, a few hundred meters. And if you do that analysis, again, relative to 2018, here we got 3.5% decrease. The state's model for how much more fuel efficiency the cars should get was 2.5% per year. So, maybe we're getting cleaner, a little bit faster than the state was projecting. So let me just tell you now the story from my student Helen, who's now a climate education postdoc in the School of Ed. So you saw that data where there was less cars and trucks on the road. They were all going really fast, because there were no traffic jams during that period. I taught my younger son to drive in that period. If you have to teach someone to drive on the highway, it's really fun to teach someone there's no cars. It's way less stressful than I imagine it would have been at another time. So here you are. This is that same approach to the San Francisco Bay Bridge. The two colors are the eastbound and westbound traffic. What you can't see here is it shows both the morning and the evening rush hour. During the rush hour, the speeds get, as often average speeds of 20 or 30 miles an hour. And what I don't know is whether that's, 5 minutes of going not at all and 5 minutes of going 40, or whether it's averaging 20. I imagine there's a lot of stop and go in this. And so we spent a lot of time thinking about the effect of that stop and go. But then you had this period, during the pandemic where there just were no traffic jams. So we thought that we should be able to go back to this inverse model and ask what were CO2 emissions and now plot them as a function of speed. So we took the CO2, we divided it by the number of cars that went by. And we took the state's model for fuel efficiency of the vehicle fleet, and they're unbelievably correlated. So, right, this is you emit more CO2 per mile traveled when you're going slow. When you're going at the optimal speed, it's more efficient. These two lines are almost perfectly parallel. Just slight offset. I wouldn't read too much into that. But it's saying that the model we have for speed and fuel efficiency is pretty much exactly right, as inferred from observations. One element of a process model describing emissions from vehicles in the atmosphere looks to be spot on. All right, so let me close out by saying I gave you a bunch of examples of how we're thinking about using this network in the San Francisco Bay Area. We have partners at USC in Los Angeles, Will Barrelson. We put out a set of nodes in Glasgow, Scotland. Sent them to a partner in Leicester. In Providence, Rhode Island, Meredith Hastings has a set out. And again, the data is live and in near real time. It's free and open. Anyone can download it at any time. And what I've tried to show you is that there's something interesting to do if you make measurements with high space and time resolution. The unique thing that we're doing is doing the CO2 and the air quality simultaneously. I showed you mostly CO2 today, but often when I talk about this, I talk about how the CO2 inventory community is progressing in its own little silo, and the air quality inventory community in its own little silo. And they both are referenced back to grams of something per gram of fuel burned. And it's completely nuts that we're doing that twice and separately. So I've been pushing our colleagues in both of those communities who build inventories to put their heads together and figure out how to do one. I think I've had some luck with the NOAA group. They have put CO2 into their air quality inventory. I think it's really important for us to be thinking about how, if we learn something about air quality emissions or CO2 emissions, we should all learn at once and not separately. They're 3 years apart. So we're learning to interpret these dense networks as more than the sum of individual instruments, learning to think about daily variability in ways that teach us about process. And we have pretty rapid timing in our ability to learn from these measurements and report out on them. So these are my current students working on this. And Naomi, I told you about, she's working on CO, Ishu on the NOx, Anna on the ozone, and Millen and Pietro on the aerosol. Thank you for your attention.
Okay, questions from Ron, and we'll start with the in-person group.
Yes, so this is very nice. My question is, are you able to scale this to region size or apply this to another city without measuring the concentration, just based on the sector, the traffic, and your results from San Francisco?
So I think, at one level you could say, sure, we could assume that all cities are the same, and we could approximately scale what we see in one city to other cities. I'd be a lot more comfortable if we had 3 or 4 cities and we were able to do that, show that they all behave the same or that they behave different for reasons we understand before making that extrapolation. So I'm not ready to make it. I would like to do this in a few cities. I think there could be a big economy of scale here. I think that a lot of the work that we've done is the beginnings of figuring out how to interpret a network. But having done that, I think we could make this more routine. And so the level of effort for city number 2 is nowhere near the level of effort for the first one. So I think we could scale this at a price point that would make sense and do this, just do it in every city.
Regarding the air quality issue, have you discussed your measurements with epidemiologists to look at public health consequences of the air quality? And I'm thinking things like lung cancer, asthma,
Yeah,
things
so
like that.
we have an ongoing collaboration with some pulmonologists at UCSF across the bay. They've been working in the city of Richmond near the big refineries.
Right.
And so we've been trying to they gave some of their patients GPS trackers. And we have exactly where they walk, and we have our inference of air quality, and we're trying to work through how that plays out. In this case, for a set of children. I don't have any answers for you yet. Okay, just that it's the right question, and we're trying.
Hi, Ron. Yeah, very great. I knew you folks were doing that, but seeing the data like this is very impressive. And I guess a comment, and then my question is, it looks like the hardware was simpler, the experiment, than the inverse modeling. That seems to be really, really challenging. But regarding also to Minhwa's point, with different cities, I'm amazed to see, if I get it right, you make the case that transportation is really the culprit, the major culprit in the Berkeley area. And so the housing or insulation or heating of housing seems to be less the source, but it would be interesting in a colder climate, or like New York City, it could be here. I mean, it's a moderate climate in San Francisco for New Yorkers. There's not a lot of heating in quotes or cooling in some areas. It could be very different here. Huh? I'm wondering the residential impact of this whole.
Yeah, so you're absolutely right. The residential heating is not insignificant in some places. And I think, the unique thing about where I am is that the residential heating summer and winter doesn't vary as much. It's not that the residential heating is not important, it's that the variation is lower. Because I'm as likely to have it be 50 outside in the summer as in the winter. So, I could get up in the morning in the summer and my heat is on. But just not as often, unless we was really cold. But well, really cold for me. We had snow at our house. It snowed in our house once in 25 years. But yeah, in other places, the winter summer difference in residential heating could be 15% of the total energy consumption of the city. It's a large number, and you would see that. It wouldn't be subtle.
May I, yeah, so it would be interesting to do that in Germany. Germany, Switzerland has a very tough residential, how should I say that? Regulations how to build. So for example, you cannot rent your apartment if you don't have a certain climate efficiency of your house right now. I mean, it's completely on a different level than here. Would be interesting to do something like this and see if it's still traffic or house.
There's 3 cities in Europe that are trying to do just the CO2 only part of what I talked about today. In Munich and Zurich and Paris. And then, the interesting thing I learned when I went to visit them last fall was they're doing like central heating. There's across like large fractions in the city. So there's one cogeneration plant that's providing then steam heating or whatever, however they're passing it all through the city. So so it's really a different model for how you heat than here in Manhattan, where every building is on its own. The question in the back.
I was interested in how other vehicle origin materials, pollutants like the abrasion of tires and brake lining, cab information, how those emissions or particles, the scaling, vertical and horizontal,
So there's not a lot of measurements of simultaneous CO2 in those things. There's lots of measurements of number of vehicles. What we know is that mostly those are pretty big particles, and their exponential scaling is really short, very, very close to the road. But,
and the vertical scaling similarly?
Yeah, they're
a couple meters.
Maybe a little more because of the thermal turbulence from the hot air coming from the exhaust and all the other cars resuspending things, but it's not. I've seen a couple of talks from groups that did really detailed modeling of that kind of thing, showing twice the scale of a heavy duty truck, rough scale on the highway. They're heavy. Most of the time those particles are too big, so they don't mix in ordinary ambient air convection the way PM 2.5 does.
I was wondering if you could comment on the meteorology measurements. You mentioned briefly, obviously, they're not co-located, but there's so much effort here on the emissions, and is there a network on the meteorology side to complement it?
There's not, because I don't have a collaborator who's interested in that. It would be great. So what I have is NOAA HER, and the large scale meteorology models that we have available, but we don't have a dense network of meteorology to go along with it.
So in the inverse modeling, if you use the like atmospheric transport model?
Yeah, so we use the NOAA HRR model at 3 kilometers as the reference model. Chris?
Yeah. I'm wondering with the signal to noise sort of that you have in all these measurements, like how hard or how possible is it to pull out in like semi-real time when something that's like uniquely, bizarrely uncoordinated or uncorrelated is happening that like could spit out curious case studies like almost in real time to figure out what the heck is going on?
I would guess that it would be possible, but there's a lot of atmospheric variability.
Yeah.
So I think figuring out I think there's we're working on it now, trying to build a catalog of all the times we saw the refinery plumes. We're trying to work on exactly that example. Sort of when do we see the refinery plumes, and can we automate discovery of those plumes? But there's enough. You might be able to do it daytime only. The nighttime is really rare. Right after through the night. So far, we've been really trying not to do that.
I want to ask you about your communication plan. So I see, 2 extremes of communication about the results. One over here, what we normally do, writing to our friends. Here's what I learned, and then we read it. Well, gee, I would like to do that and do it better. Then on the other side, there's the Ron Cohen digital billboard, the Bay Bridge, that says, here's what they said they were going to do, and here's where we are this quarter. And do we have any thoughts that, you know, if it's not as good as we promised, that would have a positive feedback? Or if it's worse than what we promised, that would have a positive feedback? And, you know, what do you think about the
Right, so-
value of public communication about
So
that?
so I'm somewhere in between those two. You know, my mother was in the state assembly here in New York for 8 or 10 years. So I'm colored by that experience of being attempting to be the science advisor to someone who was actually a legislator. And it didn't work very well. They're pulled in all kinds of other directions by.
The legislators don't all love you.
That's true. Like, so I had like the best possible opportunity you could imagine, and I was still ineffective. But what I've been trying to do is trying to talk to people in the sustainability office or in the office of someone and figure out, you know, is there something we can do to be helpful from their perspective? And to be honest, we haven't gone very far. The couple of people I've tried have said, I have a script from the UN, and I'm just going to follow the script. Why do I need you? They're not totally persuaded that my answer is useful yet. So I think what the strategy I've been employing, and it's, you know, because I would rather write the papers talking to you guys than spend my time with the legislators, to be quite honest, is to really show that we've got something that works really well. And if we've got something that works really well, then I can find some public policy colleagues who are, you know, more naturally speak that language, and we'll build those connections. And I'm pretty confident that that could come. The public policy research community at Berkeley, they speak enough of my language that I can reach them, and then they can do the translation to those people out in the policy world. That might be my best chance. But it's a great question, Paul, and I'm really, I think the other way is if we had a dozen cities, and then we could build a science community and sort of get those cities, the legislators in those cities to compete with each other and engage with each other and us, and there'd be some scaling that might work better than trying to do it city by city.
Well, we'd love to see a similar network here in New York City. So I don't see any hands up on Zoom. We've had lots of questions. Steve, go ahead. You get the honor of the last question.
Okay, thanks. You showed the local perturbations against the global CO2 background. So are you able to discern any changes in the global CO2 background for your minima, and how might that compare to other people's measurements?
No, I don't think our calibration strategy relies on sort of fitting those local minima to each other. So I wouldn't want to say we have one site in the network that's referenced to a tank instrument, a much higher quality instrument. So I could tell you what you see at that one location compared to the global background with high enough confidence to say something useful. But mostly that hasn't been our target. I don't know that this is the best way to look at it.
I mean, you in some way, like you're saying, your aerosol signal falls off of the kilometer or whatever. It's not like, well, maybe the big stuff, the big particles that you referred to in answer to an earlier question, but the little stuff, what you're seeing the fall off of is not the amount of materials, just the dilution into the
Exactly.
background.
Yeah. And the same for the CO2 and the gases. Absolutely.
Okay, so we have all earned pizza with the speaker, especially the students. We assume that all students are hungry and that they are interested in the 5 food groups, eating 5 different kinds of pizza. That's it. So we will see you in just minutes in what we now are calling the Swanson Room next to Masick in Challenger, and for pizza and casual conversation with Ron. So let's thank him again for a great job.